Hello, everybody. This is Daniel speaking, and welcome to another part of importing any tool components in ToolKit. This will be part 3 after a short break of these webinars. We decided to show you how to import turning tool components this time. As I was having tons of requests on different kinds of shape of holders, shanks, and insert, it was extremely difficult to satisfy all of you and show you all how to do it step by step. But I decided to make a list of the most important ones, and based on those, you will be able to basically define any tool components from there. And from the last webinar, we also there was a tons of requests on to explain again how the drive unit type works in the joints. And basically, I'm going to start my presentation with this slide, okay? And let me go to this slide quickly. As you note, any of the holder have, once you click on particular joint, it will have basically the drive unit type, which basically you can note in the drop-down menu, there is 4 different types of these, and they are extremely important how they will be later on displayed in the tool view, and they have very important a rule later on whether you will and how will use this drive unit. So basically, we have direct, we have not driven, we have the self drive, and we have a gear itself. Okay. I've seen that for most of the holders, defining the not driven and self drive was never a problem, but understanding how the direct and gear works, I'm going to clarify right now. So let's start with a direct. In my first webinar, I've used this example with HSK holder, a few extension shank and shank itself, and the tool itself. This holder example over here, we have to define the drive unit as a direct because it is directly connected to the station drive unit defined in the VMID. So no matter what station drive unit is defined here, the holder will directly transmit that that drive unit to the lower level component. So after this holder, it will, if it's selected as a direct, every component that is below that, it will take its property, and if this one spins, every single component will spin afterwards. So this is extremely important to understand. Now we have also a lower component, and we said in the beginning that we are going to use it as shanks in the icon of the toolkit, and it is extremely important to understand that shanks actually don't have any drive unit type properties. So they will take the property of the holder itself. So whatever you define it there, they will use it as the last element here. It's the holder itself. After that, it goes only the shanks. They will use the latest used over here. Right. Now we have easy example where we have, I just purposely put here 2 different types of turrets, which one on the left is a revolver, on the right it's the B spindle type with a B axis. They both have the station drive unit defined. They both can run live tools, and because of that, taking this tool, of course, running it with some RPMs will of course spin these holders. But if we define these holders as not driven, they will be not driven, and therefore they will not be revolved around the spindle axis, or let's say more precise, around the station axis. Yes. So these not driven, you can use for any turning turn drill holders. As I give here an example, on the left side, I put all these, they're all not driven. And on the right side, it's also the one that it's not driven. The third one is the multi-jet. Here I put it from the multi-jet as example. It is a real good example of it is a self-drive. It basically overrides the station drive unit that is defined in VMID. So for instance, if we define like our spindle can run 12,000 RPMs, and if we put this holder and we say it's a self drive, we put the property of the self drive, it can go, for example, 30,000, 50,000 RPMs. Basically, it overrides. It kind of behaves like a direct, but it has their own spin properties. Everything after the self drive, it will be basically be revolved. This is also very important. On the first webinar, I mentioned here this option of revolve to a holder for the milling. So basically, it will have an influence to that. And the last one that I also shown in the previous webinar, this is how I ended it, showing the angular holder. Here we had basically 3 different elements where I call it like HSK 63. Here I defined it as a gear, and then we had the C component, we had the A-axis component. All of these 3 behaves like a gear. Basically, in the last webinar, I changed this from gear to not. This 2 was not driven. This was completely wrong. Basically, all 3 has to be defined as a gear, and I'm going to show you this after this slide. Basically, the idea of the gear is to transmit basically to transfer the station drive unit to another tool component within the gear ratio. So the gear ratio is extremely important. And after the holder, we will have another joint, and the next a holder component will take that as a main drive unit property. So it will basically the hierarchy here is very important. So the top one is important, and having the gear ratio within the final gear ratio, it's really the final gear ratio depends on all components within, who is defined like a gear ratio, and I'm going to show you with the live example. So let's get started with this. I'm using the same part, convenient for showing this feature. And the last point where we stopped at this one. Let's remind ourselves how it looked like. I will just go mounting to the upper station here so we can all see it. Here I put it like -20. And as I've said earlier, the angular holder itself was defined like a gear, and this one is not driven, not driven. Okay, let's modify this for a moment. But before I start modifying, let's see what is our drive unit of this station. So let me go to the VMID for a moment. My drive unit is defined like 20,000 RPM. All right. So my first component, it's angular holder here, where our property of it's defined like maximum spin of 10,000. All right. So it means I cannot define the RPM that is higher than this value. Okay. But for instance, for my C1, I would like to define a different gear ratio. So of course, I can change the property of this holder in my tool component library, but this time I'll just break the link and define its properties over here. So I'll just go to gear, and let's say I'll put my max spin of the 5,000, and my ratio will be 2 to 1. Also, the ratio can be defined like 0.5. This is equally the same as 2 to 1. Okay. Right. Now for the A-axis component, yeah, we can say like this. I will break the link. And again, I will put a gear where I'll just say my max RPM, it's 5,000, and my ratio, it's 1:1. Okay, I will not change anything else here. I'll just accept it. Let me find one job which will be a proper one for showing this. So I'll just take this tilted surface over here. Let me find a job for it. It is over here. So I'll just edit it. And let me select this angular holder. I'll select this cutting point. I have it over here. Let me go to the machine view. Let me recalculate it. Great. Looks perfect. But what about our spin? You can see that as we have defined it as a gear, it will show us the final gear ratio, basically the final spin that we can actually define. So it goes from 0 to 5,000. So we cannot define more than 5,000. As you can see, trying to define any of the value higher than 5,000, it will basically cancel that spin. But what this means for our drive unit defined on the turret. So I will leave it as 3,500. I'll just calculate. Actually, it is already calculated. So I'll just generate the G code. So this is my channel 2. This is my channel 1. And over here, you may see that my final output for my B-axis turret, it's actually 7,000 because we defined one holder which ratio was 2:1, and which is multiplying whatever actually I defined here in the for the spin rate. I hope that now it all makes sense for you. Also, what is important for the gear, I've said that it will transmit all drive unit, to the next level, but of course it will also not make it spin. So basically selecting it, it will just spin the final model and it's all shanks that are beneath it. Okay. And now let me show you the very first tool, turning tool component that I'm going to use in this project. So as I said earlier, it will be, let me just summarize it a bit. On the very left, I just shown you what we have used in the past to what was the coordinate system of the particular STL component for the milling cutter export. And on the right side, you can see the turning cutter export. The main difference is that for the turning cutter export, we need to create the coordinate system that is on the top. The Z, it's always normal to the surface itself. But this is not it. This is not the only fact. Another one is the shank itself and the joint that has to be defined there. And we're going to that in the next example. So let me just open that one. I have prepared here one tool. It is the HSK adapter square shank holder 45 degrees here. And let me just see. There is a couple of questions here, but yeah, of course, I didn't say this in the beginning, but of course, everything what I'm doing here, it's basically recorded and it will be available as all previous webinars in the download section on the website. And of course, all the components that I'm using in this webinar, it will be attached there, including the presentation file as well. All right, so here I have this holder. And what you can note is that we have basically three components. Is the holder itself. We have the shank, square shank, it's 25 mm. the width and also in the height. And now over here we have the third component. It's WNMG. It's the 8.8 millimeters of the radius over here. But what is there are two things that is very nice to this. It's first of all, it's a 3D model, okay, itself. So we are going to define real insert with as a STL, okay, how revolutionary that is. And the second fact is that in comparing to earlier versions of SolidCAM, this time we can define the insert, turning insert, that it's not really parallel to the it's not in the XZ real plane. Okay, so you can define the real angle that is really how it is really in the holder and the shank itself. As you can see, it is not parallel. It's not in the XZ plane exactly how it would be in the case when we use parametric tools. Okay, so let's see what is the differences between doing all those things for the milling cutters and for the turning cutters itself. So the first thing first, I already defined one holder coordinate system here. So this is a pretty much standard, right? And I also defined a joint where we are going to connect our shank. And basically, I'll just hide it. So you see, it's nothing so special. It is in the corner here. And basically, this will be our first component. And let me just export it right now. Or actually, let me just define all of these, and then I'll export it at the end, as I used to do it earlier. So the shank itself. So we already defined also, I will use this coordinate system for the shank itself, even though I see it's not perfectly fit there. We have 1 mm difference here, but it doesn't matter. I will just leave it as it is to simplify this. The next thing is to put the joint coordinate system of the insert. Now, the joint coordinate system of the insert is the crucial part and is different away than the milling one. It is connected, it is set to the center here. So I'll just define it here in the center. I'll just click OK. So this is my point of the joint. And the main difference is the one that the normal plane, it's not the Z as we used to see it in milling, but it's actually a Y-axis. Now, there's a big reasons why we put actually the Y-axis, because we want our plane to be actually in XZ to follow the turning rules that are generally known for all of us. So we just put the normal Y, X and Z component that you can see as usual is not important at all, especially for the insert itself. So we will leave it as it is. Now for the better organization, I'll just change this as insert the joint coordinate system. And now I'm going to unhide insert, maybe to hide all the rest, so we can focus on the main part for the insert. And I'll just hide this one. And I'm going to create, as usual, the point in the middle. Also, many people ask me, okay, where we need to put the coordinate system. So actually, it is not so important. You can put it anywhere here, but try to put it, as closest to the middle. It's not the general rule. Even if you put it here, it will completely work. It's not that important. The most important part is how you put the coordinate system, direction. For the output of the insert, you just put the Z-axis normally like this. Okay, so the joint is in XZ plane, so this is a rule. But for the insert itself, it's Z up. Also, the X and Y in this case, this is not important. For better organization, I'll just put insert coordinate system. Right. Let me unhide the rest. So let's start with the exporting. So yeah, I just unhide it, but let me now hide it again. So I will just save it as, and yeah, the name itself. So I like to be organized, so I will just copy the name, do save as. I will use the standard folder that I used to do. I would create a new folder. I will call it turning. So we all following this. I'll call it HSKT, and my STL would be the name itself here. I will go to the options. Nothing so special in this case. I'll just select the holder. It's not fine. I'll just use course here. Just click OK. I'll click save, and yes. First step's done. Let's hide this one. Let's unhide the shank. So I'm going to, by the way, for all of you also, I see the question like how I'm hiding and unhiding. You can hide with a tab key, okay? But if you want to unhide it, you can leave your mouse wherever you are and just where you think your component is, you can do a shift tab, okay? So you can also unhide the component as well. Where is that? Yeah, so shank. Put the name, file, save as, and let's go back again there. Webinar turning. I'm going to call this just a shank. It's completely fine. And I'm going to go to the STL, change the name, options. It's the joint itself, as we mentioned earlier, and just save it. Okay, and the last component is the insert itself. I'll just, again, go here, export it. I'm going to do a little bit faster, so no worries if you don't see it on your GoToMeeting. It's a bit faster, I assume, but I think it's okay for you. Insert, and I'll say STL, put, this is the wrong one. I cannot now modify it, so I'll just type it manually. Options, and I'll just modify this to be fine. And of course, I will just select on insert coordinate system. Click OK, save. Done. All right, now I'll just unhide all. I don't need it so much, but I will need it in a few moments. And as usual, let's go to the toolkit. And I'm going to add this as a tool component. I'll just use the same TLV file that I used before. And I will organize it a little bit now. So it starts to be a mess, and I want to show you one feature that I really like. Probably you've seen that all our tool components that we used in this project, they're really connected to this particular file, webinar.tlv. And they have this kind of small icon of linked. So everything what we have modified, if we modify anything here, it will also reflect to the CAM part. Now, somebody asked like, okay, what will happen if I try to make a new folders and now there are different kind of links now? So would that affect the CAM part? So the answer is no. So you can now in any moment create a new folder. And for better organization, as I said, you can make a milling, you can make a turning. For all milling, we'll just move it here. And the same we're going to do with the shanks and holders itself. So just to keep it better organization. Right, so, and of course, also for these demonstration purposes, to always be focused on the turning, the milling, it's not any more important at this moment. Right, so let's start with the holder. So I'm going to, again, select the holder, nothing so special here. Webinar, turning, and select the holder. I forgot one thing to do. I'll just rename this and rename the holder itself. All right, now we're coming to a pod where I want to actually see my holders, and I want to use the SolidCAM utilities. And in this case, I'll just select the holder and the joint. Just click. So how I'm doing it, again, I'll just repeat. Click on the first one, hold the control key, select another joint, and just click on the coordinate system metrics. Here it is. I'll just go to the connection. And for my joint, I'll type those values. So it's -1, -54.6. And for Rx is 180, 135, and this one is 0. Don't forget, we came to the conclusion, so this is a turning tool, so my drive unit type in this case will be not driven. Don't forget to do that. All right, so this is for my turning tool holder, and now we are going to use the shank. It's a square shank, so I'm just doing a drag and drop. Let me do a connection, of course. You can also minimize it with Control Shift. So for all of you guys who don't know about this, for the active window, you can do a Control Shift in any way, so it will kind of minimize, so you can play with this. It's kind of nice. And now I'm just going to clear the selection, and this time I'll just click on the joint, put on my master, and this is a crucial point. The next one, it's insert joint coordinate system, where my y-axis is normal, okay? And this is my slave now. Right, so all the properties are over here. So let me write it, 24.7, minus 4.3, minus 113.7. Then we have minus 11.87, 44.381, and 8.363. Crazy values, right? Okay. Let's see. No, that's not the right one. Did I select the correct joint? Insert joint coordinate system. Do I have to apply something? I make a big mistake, but okay. So let's go to the 3D model. And again, to the webinar turning, I forgot actually to select it as a STL. I hope it will not change and just change the shank name, and he'll leave all as it was. Okay, so probably everything will be okay. Yeah, everything is fine. So here it is, guys. And we have the final step, just insert the insert. Nothing so special, I will just move the profile. I will, instead of parametric, I'll select the 3D model. I will go to the webinar, turning, and insert. Okay. Change the profile. Renaming you can also do with the F2 key. So it's kind of faster than doing the right key and rename. So just clicking F2 and it immediately goes to, it's kind of Windows feature so it also works in the toolkit. Here's the insert. This is how it looks like. As you can see, the real STL here, not a parametric one. And just save it and just accept it now. Let me go through the questions. I see kind of a lot of questions. Can you comment? Okay, I'll cover that questions actually later. All right, so go back to the project. And I will not this time define it in the assembly, but I will just directly go to the part 2 library. And let me open the library that we have this defined. I will start, as I'm using the advanced view, I'm just going to insert directly the holder. So I will start from top to the bottom. And then I'll define the shank. And then I'll just drag the turnkey insert itself. Okay, let's see how that looks like. So far, so good. There is only one exception, that the insert itself, as you can see, it's under some weird angle. This is because it took the property of the previous profile. So you need to modify this angle over here to something that it suits the most. And this angle is actually 60 degrees, as it is a triple side of this. So 60 will be the best. And here it is. Okay, so let's now discuss about cutting point. And talking about the cutting point, particularly the offset itself. So this is the things that we never seen before, and I want to cover it at most. And let me, in this case, I will just use also show high tool picture, and I will just kind of move it over here so we can actually see it. And also toolkit over here, I will try to maximize as much as needed. Also shrink this and organize it. And of course, to turn on the tool, the machine preview. And I will show you also, guys, a couple very nice feature over here. Going with your mouse to the machine preview, it will highlight this window. But if you move your mouse to your tool viewer, you don't even need to click on it. It will just automatically like show you on the top. It's kind of very useful when you want to, focus on the particular window. And I will just go to and mount on the station. And here we have it over there. Okay, I will click again on the cutting point. And why the cutting point is so interesting to me is to understand the main features that we have over here. First of all, this tool, it's mounted on the spindle in this direction, and because of that, we automatically recognize where will be actually the origin position according to this picture over here. Now you need to understand that this A, B, C, D, E, F, G, and H is not actually 1, 2, 3, 4, 5, 6, 7, and 8 as it is really on the machine. You need to understand that importing any STL component in SolidCAM actually don't see the sides. It's completely impossible. It's just a 3D geometry. So you need to very focused on what you actually see here, and the coordinate system that you see actually here correspond to the coordinate system that you can see here. So the very first step when you import the STL of the insert is to correctly set the measure orientation in the case when you have the B-axis. And this is why I took actually this one, because it's 45 degrees. And what I would like to have is the angle over here, like this. Now, in the previous versions, we allowed user to define, this orientation, as you can see here, but this is not really actually what will actually happen on the machine. On the machine, we really need to say what is the measure orientation when we actually measure the tool. So I will click over here. You have an option to measure orientation. I'll just click on that one and put here the angle and find the angle which I'm actually going to use when I really measure this tool. As you can see, changing any of the angle, it automatically switch the offset to the position. Okay, now we have it over here, and it automatically select the one that is along the X. It's also mentioned it over here. Now I like to use this one. Everything is nice, and I want to show you a couple of other options. If you're not satisfied, you need to understand also that because it's STL, the SolidCAM actually recognize more radius origins, let's say so. So it can be this one, it can be that one, it can be another one. And if by default, the one that you exported, it's not automatically selected to the one that you have here. For instance, it can be easily happen that it exported over here. In that case, you can use origin position, and everything that is detected by exporting, SolidCAM will show you over here. So you can see that SolidCAM automatically detect more cutting position. So in this case, I'm satisfied with R1, but I'm not satisfied with the angle that is actually taken. So I'm going to take this, and I want to be in the corner. So that's this one, and this is the proper point that I actually want to use. There are also 3 more options here that you can also shift it if necessary to 0.8, 0.8, and also there's the radius of 0.8. This option is extremely important in the cases when you don't have really the radius, or if you have shape turning tool that I'm going to talk in the next webinar. In that case, it is important to use this and to properly define this point. I will show you that in the next webinar. For now, I'll just use this one, origin position, minus 45 degrees. I'll just click save and exit. All right. I'm going to use this tool, let's say in the face turning. So let me turn off this. I'm just going to replace existing tool that it's used there. I'm using this one over here. Let me just go and select other. And I'll just accept it. Oh, not that one, sorry. The one that we have used. Mount, maybe. I don't actually really have to mount it. You can just select at the cutting point. And here we go. I'll just select the one that I'm using. And now open the machine preview. Let me just calculate it. And here we go. That's it. Now, you may ask me, okay, Daniel, why we actually used measurement orientation and measure our tool in specific angle if we actually can really use any of this angle later on in the job. And here we come actually to, let me go to the presentation, switch. In SolidCAM 2021, we create a new parameter in VMID, which really depends from machine to machine. The one that can actually change the angle and automatically handle the offset, or the one that cannot automatically handle the offset. For example, this parameter is located in the VMID controller definition, general, and there you will find inclined tool nose position. By default, it's set to yes because in earlier version, we always allow this to user. It is under the user responsibility to select the proper one. But in today, I would prefer that this is set up right. For instance, on the magnetic anti-Grex, every position has to be measured. You know, in that case, I will definitely only set to no. So it only filters me the possible angle that is actually measured. If you want to use the same tool with a different measurements, you can do it. Just copy the same tool item and select the different angle. No problem to use it. So you will have to define as many tool items, different B-axis orientation and measurement orientation if you want to take any other offset. So let me go to VMID to show you this feature. So now it is set to yes. I'll go to the VMID. General, and I'll just say this parameter to no. Also, there is a description about it. I'll just save and exit. I'll go back to the job itself, and now you can see only one possible tool angle can be used. I hope this makes sense to you. And as a next example, I have prepared a Pico turning tool. I found it that a lot of people are asking this. So my next example, and the last example for today's webinar, would be the Pico turning tool. Let me open that one. So I have the turning. The tool that I'm going to use is the Pico. This tool actually comes with, how is it called? The clamping on the shank, but I already have that, so therefore I will be just focused on the whole tool itself, and I'm going to open it. For the project, I'm not going to use this one, but instead I will use Swiss type machines from Star. It's the Star SR20J Type C. And let me just quickly show you how this machine looks like so you have a better overview. So it has it has one gang tool which allows you 6 turning tools over here. Some tools, front drilling, or also turning tools on the front, and many radial tools on the side in the channel 1. Also, there is a possibility to attach the holder, which will allow you to have the front face milling operations. And on the sub spindle, we have 3 live tools and 1 turning tool that we are using in this example. And I'm going to change this turning tool itself to the one that I've shown you for the Pico, for the internal boring. But in this case, it's for the facing, and for that purpose, it will be completely fine also to show in this demonstration. So let's go to that tool itself. And as you can note, usually when you download it, I've seen many examples, and it can come in 2 different variations. The first example that I've seen is that these 2 both solid bodies, as you can see it here, they are both matched. Okay, so they are merged into a one body. It is clear that not whole tool is used for the cutting, only a portion of it is used for the cutting. And this example from ISCAR, it already has prepared the area or the volume of the tool that it's actually used for real cutting. Okay, so in this case, this is the only preparation that you actually have to do. Everything else is exactly the same as we already have it before. So let's start with this example. It's nothing so special. Of course, I will also analyze it if this tool has the radius. If there is not, you can also feel free to insert the radius there. It doesn't have to be 0.4 as in this example, but you can put a little bit smaller one if you want to make it smaller than 0.4, of course. But the main idea is that the SolidCAM analyze the radiuses. If you don't have the radiuses on your insert, the SolidCAM will not be able to detect where is your actually cutting point, and therefore you'll have to define it manually. Okay, so this is the only thing that I should input. So as you can see, everything here is prepared. I didn't touch anything on this example, so I just downloaded, and in this case, I just defined this coordinate system to save time. But basically, I will just create point over here. I will just basically repeat the same process as I was doing before. And my first coordinate system would be Y up. And this coordinate system I will call insert joint coordinate system. And I will basically select the same joint. Maybe I can hide this one. Select the same point, create another coordinate system, and where my Z-axis will be up. And this will be my insert coordinate system. Okay, let's do this quickly. I will hide this one, File, Save As, and let me just go to the metric, webinar, turning. I'm going to call this like Pico folder, and this will be up, that new folder, but a new file, STL, options. As it is a shank, I will use a course here, coordinate system 1. Click OK, and I'll call it Pico shank, even if it's really not, but I'll just call it like this. And the next export, I'll just unhide it, hide this one, file, save as, metric, webinar, turning, Pico, and I'll select to the STL, check the options, I'll go with define. And my coordinate system, it's basically the insert coordinate system. I'll just click OK. I will go to the Pico insert. Yes. Perfect. The only thing is now just to go back to the project. And in this example, I will edit also. Let me first put it into 2 components. Why not? Again, go to the webinar. I don't have any holder for now, so I'll just be focused on the shank. And my holder I will use for the project that is already there defined, so I don't have to do it. So my shank, I will just, this time it's a round shank, 3D model, webinar, turning, Pico, and I will select the shank. Of course, now I just need to select the proper joint and the coordinate system. And for that one, I'll just hide this one, go to the SolidWorks, and I'll just again select the coordinate system and the insert joint itself. So this is important. Right, this is the master, this is the slave. Make sure that this is correctly defined. And let's put some values, minus 1.2, minus 0.2, minus 36.3. Here we have 4.911, 0, and minus 3.382. Let's check this out quickly. Looks fine, perfect. And the next one is the profile. And I will be just selecting as a 3D model. Great. I'll just save and exit. I don't need this 3D model anymore. Go back to the project, edit. Great. So which is the tool that I'm going to use? Let's again, guys, go over here. Is the tool 21? We don't see it here, but it's tool 21. So let me find it. Here it is, 21. We have the holder and we have here the shank. So I cannot currently remove the shank as I'm using it. So I can just, what SolidCAM and ToolKit allows me, it's so good. I can actually now put additional shank and profile and select it in the job and later remove this shank. So webinar, start with the shank itself, put it there. I can see it, nice. And just let's put a profile. The profile itself is not in the perfect spot, so we'll have to modify it a bit. For machine view, it's not good for that, so I'll just focus maybe on the tool viewer. And tool viewer, let me close machine view, and let me go to the, let's put this to 0. And I really don't remember that I needed to put the coordinate system here. It's completely not necessary. It should output it correctly from the, but okay, I'll just leave it for now. It's 35, seems to be it's 35. Okay. And play a bit. I will not make it as perfect as I would like to. I'm missing here an option to make it nicer. Something like this. And on the Y, we are close. I'm missing you guys really to how you can do this quickly for the next webinar. And a little bit on text. Okay. Here we go. Seems that it's like reversed values. I'll check that. That's it. We just need to check our measuring position, which is not correct in this case. So I'm going to select my cutting offset. I'll select my origin position. And in this case, I'm going to use this one over here. I'll just save and exit. Let me go to the face turning tool itself. I'll go to the tool, select the shank, sound calculate. Let me first remove it before I show it to you in the preview. So the tool here, so we don't need now anymore the shank. And now, as you can see, because I selected another shank, now I can freely remove this one. Great. Let's go back to the job itself. Simple face on the sub spindle. It's pretty long. I can make it, of course, shorter. Let's go to the preview. As you can see, it's very perfect. It also detects the rotation. You can see it in the data. Sorry, in the tool here, it's choose the counterclockwise here. Everything is perfect. I can also rotate it, maybe start from the X negative if I want. Yeah, why not? We have a few more minutes. I can do that. So for instance, I would like to start from X negative, so I can basically rotate it for 180 around the Z position. Great. But in this time, it cannot start from X positive, but instead I will choose, X negative. There you go. And again, I'm getting counterclockwise here. All perfect. I can simulate it. And it starts from the X negative. Guys, I hope you enjoyed this. I hope it was very informative. I can see already that there are a couple of potential questions like how we can manage the positions better. I'll come back with that question. Let me see the questions here. Where are the? Where's the chat now? Let me see it. Questions? Why don't I see questions? Here we go. Yes. Okay. So there will be, okay, as I earlier mentioned, there will be custom shape turning tools in the next webinar. There will be multi-position tool. There will be also indexed holders, okay, and there will be also with different spindle orientation tools. Just waiting for you guys in the next webinar. Thank you for watching this one, and see you in the next one. Thank you and see you. Bye-bye.